Hello again, Math Ninja here. I know I haven't been presenting for a while, but last quarter I was relearning a topic that was very difficult for me. Differentiable manifolds. I like set theory. I like logic. Number theory is pretty cool. The introductions to those. I like statistics, but geometry and topology have always been, personally, the most intuitively confusing subjects, even though they're probably the most intuitive of mathematics. So today I'm here to answer a response from one of my friends. You see, he's want to apply to college, and he wants to understand what is mathematics like in college. So, as an undergraduate, I have, in mathematics and EE, I have a little bit of perspective. Maybe it's different at other colleges, I don't know. Maybe. But there's a big leap when you head from high school, for example, American high school, not foreign high school. From, for example, Calculus BC, Calculus AP, to college mathematics. So, this is not really a lecture. This is just colloquialism, just conversation. I don't feel like presenting anything because this is actually our spring break, and I deserve to relax. Relaxation is very good for the chi. So, college mathematics. I remember when maybe I should explain. There are two types of math majors here at Stanford. Two types of mathematics. One is the engineering type. Now, this is not an insult to the engineers, because engineers, they work very hard. They have to take maximum units every quarter in order to finish. They are very tough people, always very competitive. Math people, they're very lazy. They just want to know how to prove things, and they want to believe that it works. Then they let the engineers figure it all out. So engineering and math, they are two different sides of the same coin, I would say. So mathematics in college. Well, in high school, everything was about computation. Sometimes they show a little proof, a little theorem. Or, for example, calculus, you probably learned the mean value theorem. You know the statement. Maybe none of you guys know the proof. In college, every theorem is important. Every corollary of that theorem is important. But especially, not only the statement, but the proofs of those statements. They are vital. See, I take 2 classes in probability. One of them, they both use the book Sheldon Ross, Math 151, and EE 178. But there's 2 main differences. One concentrated on proofs. The other one concentrated on computation, combinatorics. So there's quite a big difference in engineering and mathematics in college. So my math major friends, they cannot compute anything. You ask them to integrate something, they say, I don't know how to integrate that. But they will be able to prove things like convergence. They'll be able to prove some of the most beautiful theorems, but they do not know how to calculate. But that's okay. An abstract mathematician follows the rules. Derive truth from what we know is true. And also, the world can change, the system can change, but the mathematician can still follow through. Which is an interesting thing. Engineering, yes. Some people who have math and engineering, their background is limited, I would say. Not an insult once again. Not an insult. So I guess that was a little bit rant on engineering and mathematics in college. maybe I should go on a little bit about that. So in my school, as soon as you enter college, you go into something called the 50 series or the 50H series, the honor series. In the 50 series, you begin off with linear algebra. Now, in engineering, this is the 50 series, Math 50 series. You learn how to compute things, how to compute null spaces, how to compute dimension, how to perform Gram-Smith process to find an orthogonal basis for a vector space. Things like that. However, if you're a math major, if you're a real math major, not when I say real, this is bad. When you're an abstract math major, you learned the definition of a vector space in an abstract form. For example, in engineering, you learn vector space as in the span of you learn the inner product is going to be dot product. In mathematics, you learn it as an abstract idea of the inner product. And you can apply it to any spaces. Let's say, for example, a very important case is for deriving the Fourier series. You need an inner product space of 1 over pi, the integral of negative pi to pi of f of t times g of t. That's the inner product of f and g. So the integral of that, very important for deriving Fourier series. And that is used on the functional spaces. Well, particularly the one that we usually like to use is the piecewise continuous function with averaged out at discontinuities. I don't want to throw in too much jargon, so let's just say, because this is I'm trying to make it colloquial, and this is not the lecture. This is just fun conversation. So that's an example. In the engineer, you learn how to compute things. In mathematics, in the abstract sense, you learn the abstract definition. You prove things from the definition, from induction, from contradiction, from proof. And you apply an abstract setting. For example, if you're analysis, a general metric space. So, one moment. So in analysis, you work with a general metric space. So my friend, he also had a different question. So, I guess maybe more about college mathematics. Is that, okay. In high school, everything was just up to calculus, I guess you could say, or include calculus. Maybe you had some linear algebra background, or maybe multivariable calculus. Multivariable in high school, I believe, kept to 2 to 3 dimensions, I would say that. They did curls and gradients, but there's a generalization of curls and gradients to higher dimensions. So that's actually another difference between, that's something you learn, I believe, in college mathematics and not in high school mathematics. But that's engineering. But then you make it into abstract mathematics, in which, in order to prove those things, we use something called tensors, alternating K-forms, differential forms. Those are quite a bit. There's an old saying in the math department. Algebra is easy, because that's in high school. High school algebra is easy. When you put the word abstract algebra, word abstract in front of it, then it becomes difficult. So let's see. Okay, I think I'm done with that rant. Now I think on the next one, I shall talk about the major fields of undergraduate mathematics.